Warning for my talk. Be careful, guys. Don't distribute. Yeah, go to jail.
All right. Okay. We're ready. Okay. Thank you all for coming. Welcome to this seminar, and it's a pleasure to have here among us today Professor Chellappa. Professor Chellappa is from University of Maryland. He at the Electrical Engineering Department. He got his MS and PhD from Purdue, and he's been professor at Maryland since '91, and he's currently the Minta Martin Professor of Engineering. He's also affiliated with the Center for Automation at Automation Research at University of Maryland. He's been associate editor and editor-in-chief of many very prestigious transactions of IEEE transactions, and he's a fellow of the IEEE and former vice president of awards and membership at IEEE, and he's co-chaired chaired many IEEE international conferences, and so it's a very big pleasure to have him here. And today he'll be talking to us about some of his work in video exploitation, and more precisely about gate analysis. I think.
Some of that too.
Okay.
Yeah. Okay.
Thank you for coming. Yeah.
Good afternoon. It's always a pleasure to visit campuses and talk to young scientists and researchers. Where will professors be if not for graduate students? Okay, right? So we live off you. Thanks for coming. All right. So the title of the talk is Looking for Patterns in Video, and so let me just give some examples of kind of videos we are interested in, and I'll present some of our recent work on that. And this is a video taken of an airport tarmac area by TSA, Transportation Security Administration. And if you have a lot of time waiting at the airport, and if you are at the place where the small planes come and go, you will see some things being repeated again and again. Before the plane arrives, the ground folks get prepared for it. They put the orange cones and kind of tell where the plane should come and park. And then the doors are open, the passengers get off, and things are taken off, and things are put back, the passengers come back and go. I mean, this just happens in a routine way. And it can happen maybe, 50, depending on how busy the airport is, it can happen 50 times a day and so on. So you have a lot of data, you can just observe it. The goal was to build a normalcy model, just to see if we can model this behavior, all right, and then look for anomalies. So this is something that we've been working on for a few years. And what you will see is that the shape of the trajectories have a lot to do with what's going on. When people get off from the plane, they all cannot wander around everywhere in the tarmac. They all have a place to go to in the terminal, and these things are kept in usually in same places, and they're going to make the same route. They take the same route to the aircraft and so on. So it's very interesting. There are some minor variations in the trajectories and so on, but the actual things that are done are very similar. Right. Now, this is a bank transaction video, staged one taken by Monique Tana at INRIA. It's a normal transaction. This guy comes and does the forms, and this guy does something with the teller and leaves. So we are interested in understanding that. And the next view graph, I'll show you an abnormal one. And this is Simon Baker at CMU. Should we shut off the lights here, or is it okay?
Because of the recording.
Okay, that's fine. Okay, so here the person is sitting in a room and there are 50 cameras taking pictures, and you make a video out of that. Depending on the pose and illumination, the images are different, although the person is the same. It's an example of pattern recognition. And if you look at this, I hope this video, right? Now, here again, you see folks coming in, and then, of course, this guy comes and then takes the teller into a room where there is money, and then they grab the money and he goes. Of course, this is not a real thing, it's a staged one, okay? So can we tell the difference between an abnormal transaction like this and the normal transaction? Now, if you want to pose it as a classification problem, you right away run into a difficulty. There will be a lot more examples of normal behavior than abnormal behavior. Thank God, right? Too many abnormal things and that become normal, then you are living in a strange world. So that means you can't learn enough about abnormal things. So the idea will be to learn as much as you can about normal things and look for outliers. Okay, so that's one challenge. And if you look here, there are a lot of bees moving in a hive, and this one particular bee that is marked is doing some strange dance. It's called the waggle dance. It went out, found honey, it comes back and tells all its buddies that it found good honey source, how far that source is, where it is located with respect to the sun, and how sweet that is, and so on. Obviously, the beehive is a very dark place, so it's all mostly vibrations and so on that's made. So biologists who are working with these bees and trying to figure out how they communicate the information to other bees would like to know when the dance starts and when the dance stops and so on. It's a very precise dance. So you can model it as a 4-state Markov chain, okay? And then you can use it in tracking that. So that's also a pattern thing. Now if you look at this video, which was taken in the back of our building, you will see one person coming and he gets into the building. That's not a problem. We are watching this area. So as cars come, we make declarations as to cars starting, moving, stopping, somebody getting off, and so on. Here we are modeling what is known as a casing behavior. That means if this guy gets out and then checks every car in the parking lot to see whether the car is unlocked or whether he can take something out, that is called casing. But if he only looks at a few cars, then we are not too concerned. People sometimes are curious. So then you have to make the distinction. Okay, and we developed an attribute grammar method for doing this, because here there are a lot of primitives, stopping and starting and moving and so on. So you cannot capture all of them just pure trajectory. It's not a continuous motion. So you have to have these short tracklets and then give attributes to these and kind of string them together to what may account for a particular kind of activity. Now, so you would have seen that not casing behavior. Now here this guy gets off and just runs into the building, one of our graduate students, So we wait for a while, and then if nobody else, car cannot move because the driver is not there. But maybe the fellow sitting next to the passenger can move and then drive. That doesn't happen. That's when we kind of then declare abnormal parking. Okay, that's it. Then we call the parking guys and they give him a ticket. Okay, so there are various things like that. In general, when you have pattern recognition, image recognition is a special case of pattern recognition. And then you can talk of still image recognition and video recognition. Still recognition is fingerprints, OCR, still faces, and so on. When you design pattern recognizers for separating these patterns, there are a couple of things you have to keep in mind, right? You're going to derive some features, right? Some representations that hopefully have discriminating power to say that some patterns come from this class and some from this class. Now the patterns themselves may undergo variations. There may be scale variations, pose variations, illumination variations, and so on when you talk about a still face recognition problem. So if you want to design a statistical pattern recognizer, then one of the things that you want to hold on to is a class conditional density. So probability of a feature vector conditioned on Chellappa. So that PDF supposedly should be able to characterize all possible features that you can extract from all phases of Chellappa under all possible conditions. Expression changes, aging, illumination, pose, and all of that, right? Now, that's very complicated, okay? But you have to account for that. There are a couple of ways to do it. You can derive features that are by nature insensitive to these variations, or when you extract some features, when you do the matching or when you do the classification, you allow for these variations. So there are a couple of ways to handle that, either at the feature level or at the decision level, okay? Now when you come to video, there are always appearance changes, because if I'm walking in a video and it's not lighted well and so on, you'll see all kinds of changes in my facial appearance. Pose, I may not always look straight at the camera. I may not always have the same expressions and so on. And also I am moving. So that if you want to characterize motion, a moving face of Chellappa, under all possible things, it's a much more complicated PDFs, right? Now, so pattern motion is the one that separates the still image recognition problem to video recognition problem. Now pattern motion can be a helpful thing, it can also hurt, right? It can be helpful if you are trying to tell me who I am by the way I walk, because maybe I have a very unique style of walking, and that's what we call as a gait analysis and gait based human identification. which is a useful thing to try at large distances, because you can't acquire fingerprint at distances beyond 0.1 centimeters. Sometimes most of them need touch, right? Iris 1 meter, face maybe a few meters, gait you can go up to tens of meters. Okay, so that's one of the things that was tried as whether human gait, although we all have anecdotal evidence that we can tell close relatives and so on, walking in a mall, in a parking lot, although we may not see their face, right? We can tell them by the way they walk, but it's still not very effective. But so in those cases, motion is critical. But pattern motion is important because most human activities involve movements. It's very difficult to just stand here and not do anything and be involved in anything. Of course, if the action is just standing still and not doing anything, sure. But that's not very interesting. So that means movement, action, movement, trajectories, and trajectories have shapes. The idea is, can you link the shape of trajectories to underlying activities? Then you can formulate the activity recognition problem as a deformable shape matching problem, shape tracking problem, and things like that. Okay, so that's where we'll be going. And of course, how do you, what is the banner that you put on this field is that in statistics, we are all interested in fitting models and making inferences, hypotheses, and so forth, based on the observations we have. So we have a likelihood, we have a prior, and we go with our inference methods. Now, in the case of some of the things I talked about, it's not just numbers. There is some geometry, right? If I'm interested in a human motion is an articulating motion, and there is a kinematic structure. Okay, so the broad field here is statistical structural inference of geometric quantities. Okay, right. So there are a lot of things here to talk about. Excuse me. The early spring always gets me with all kinds of cough and cold and everything. All right, so I'll briefly describe some ideas in terms of appearance models and so on, basically representations, and then we'll talk into the actual mechanism. There's one view graph here that it always gives me trouble, and nobody has figured out why. But if I get into trouble, I'll go and start again and I'll be fine. Okay, so that's not this one, the next one. In terms of decision rules, again, the Bayesian method is familiar to most of us. Unsupervised clustering, sometimes you may not know much about where these patterns are coming, and so you just want to separate them into different clusters. So that's unsupervised clustering. And Petri nets and extensions provide a nice way of incorporating structure, and we have done some work on that with a computer science colleague at Maryland, Professor V. Subramanian. And parser is what we do for the parking lot examples, where we design attribute grammars and construct stochastic early parsers and things like that for figuring that out. Okay, so I'm going to focus on a couple of these examples. I talked about face recognition video in the yesterday talk at as part of IEEE Signal Processing Society Distinguished Lecture. So I removed that few slides because Professor Krim has already heard that, and I didn't want to.
Don't mind me.
No, that's okay. So let me start with. Oh, see, I told you this one always gives me trouble. Okay, it says send error report, and I don't want to send any error report. Now, what I want to do is I'll go here, and then I'll go here.
Blame it on Bill Gates.
No, this is being recorded, so I'm not blaming anybody for anything. And if in case that was recorded, that was Professor Krim and not me. Okay, I'm sure the microphones are sensitive to have picked up your. Okay, that's all right. This happens every time, and I've tried to figure it out. But I can also showcase my skills with PowerPoints and so on. Right? Okay, so this is what I was interested in, and maybe I can go in this mode, and it usually works. All right, see, these are the various representations I can think of. The B dance can be represented using a 4-state Markov chain. Well, the 4 states are straight motion, turn, waggle, and motionless. And then if you have enough training videos, you can actually fit a Markov chain to that and then use that in tracking. And if a human gait analysis is of interest to you, then you can background subtract a walking human, and then you can have landmarks. These are just 2D frames. You can have landmarks along the silhouettes and then see how these landmarks dance around when the person walks. It's possible that they dance around differently for me compared to you. So if there is any discriminating power like that. This is the tarmac data where the trajectories have meanings in terms of what happens, and so on. And this is another example where as a person walks, you can plot this width vector, okay, like these guys, okay. As you can see, where there is hand swings and leg swings, the vector is pretty large in terms of how separated it is, right? Now, each waveform comes from one frame. So if you have 60 frames like this, you have 60 waveforms like this. So can you characterize this? It becomes a kind of a signal processing problem. Now here, what we did was we had a set of non-overlapping cameras around an oval track at an army base, and vehicles will come in the first camera, and they wanted to know whether they see the same vehicle in the next camera and so on. If you don't have overlapping fields of view, then you lose it. The next time you detect it, you want to make an association whether it's the same thing, right? Now these vehicles have their extended objects, so they have features. So what we can do in the first camera itself, using the video and some ground planar motion constraints, use a factorization approach to build a 3D model of the vehicle and then provide synthesis, novel views of the vehicle at multiple cameras, and so they're all ready with the model, and when the next vehicle shows up, they'll detect it and they'll be able to verify is this the same thing that we have seen and things like that. So these are various kinds of representations that are talked about. Of course, recently computer vision researchers have started looking at manifolds and so on for various applications, and in one of our applications it comes very naturally. What we do is when we take the passengers walking from plane to here, or even you take the silhouettes of the walking human, get landmarks, and you do the Procrustes, it always goes to the other one. Wait guys, I'm not done yet. Procrustes distance, that means you take the scale variation and the translation variation in the landmark feature points. One can show the resulting features will lie on a shape sphere. It's a unit sphere. So if you have my landmarks and if you have Hamid's landmark, and if they are sitting in two different parts of the sphere, next time when I walk and you want me to see where mine lies on the sphere, the distance measures cannot be Euclidean, so they have to be non-Euclidean. And so what are the appropriate measures for it? In the early days, what we used to do is we used to dump all the trajectories onto a tangent space, which is here at the mean of the Procrustes distance, and then it will become trajectories on this tangent space. Then you can fit your time series models and then use available methods for separating one model from the other and so on. But now you can do better than that, okay? And then the idea of abnormal activity. So if all the normal things are somewhere here, and how do you define an abnormal action? If you are dealing with IID, 3 sigma rule usually works. Gaussian case, you can say that if something is bigger than the 3 sigma from the mean, then you can call it an outlier. When you have time series kind of data, even small amounts of outliers can cause problems. This has been known for many, many years as part of robust.
But physically, what can you say is abnormal or abnormal?
Abnormal.
Physically.
A passenger not going along but kind of wandering around in the tarmac area is an abnormal thing. And they don't like passengers going near the luggage thing. So if you're watching all of that, somebody getting off and going to places that they're not supposed to go. On the other hand, a ground personnel, he can walk all over the place, right? So you have to mark them and you have to make these decisions. Okay. And in the case of bees, if the waggle dance is not good, that's abnormal. You must have seen the 60 Minutes show about how honeybees are all kind of disappearing because they're getting some disease in the whole colonies. They go and they don't come back. That's very disturbing because honeybees have excellent skills in navigation. They can go 2 or 3 miles away from their hive and they use landmark-based navigation. They can come. They can even navigate over stretches of water and so on. And if you want to know about what honeybees do, you got to keep track of Professor Srinivasan's work. He used to be at ANU in Australia, Canberra. Now he's at University of Queensland in Brisbane. He's a world leader on that. And we came to know of his work as part of our involvement in an ARO, Muri, on designing hovering micro vehicles. And of course, when you have very small micro vehicles, right, they don't have a lot of computing power. So the natural question is, can we learn something from what the bees do, in terms of navigation and perching and things like that, and understand how they can design such algorithms for micro air vehicles? Because bees also have very, very small sized brain, but they do a few things they do them well. It's really fascinating to learn about how all these things do. I mean, we are not biologists. I don't like bees. I don't. They sting you if you're not, and they know if you're afraid of them. They come after you. Yeah. So when bees are buzzing around you, pretend to be very bold and so on. They read expressions. They read expressions because they always seem to chase me. Anyway, okay. You know what? I'm moving forward. Okay. Let's look at the problem here is to find out when the dance starts and stops. Okay. So it's an interesting tracking problem. What we thought we could do is we will use some anatomy, but then anatomy is not very useful on its own because all bees look the same. So how can you use that to separate one from the other? But we still use that because for the bees, the motion is constrained by its anatomy. There is a head motion, and thorax motion closely follows that, and the abdomen motion follows it. So you can have a little kinematic chain like the human sort of thing, and that's a useful constraint. And then if you look at what the waggle dance does is this kind of for amusement, it codes all this information, direction of food, and you can fool them, and you can do all kinds of tricks, and they overshoot, they undershoot, and so forth. Okay, there's even a dance for them to tell that there is all the barrels are full, don't bring in any more honey. So the big, otherwise they're very busy bringing in honey, right? Okay, so the idea in tracking is we use the Bayesian method. So you have to have a likelihood, you have to have a prior. Okay, the prior we use is the prior that comes from this Markov chain, because as I said, a bee dance can be described in terms of 4 states, and then you can actually estimate these transition probabilities. And then we have the likelihood we define by the kinematic model and by the actual measurements we are taking from the video. This is an easy problem. It may look like there are a lot of bees running around, but then the camera is looking from the top. Okay, so there is occlusion, but it's not very serious. Unlike if you have a situation where the cameras are mounted on the ground and you are looking and thousands of people walking like that, then it's a big problem. Occlusion is really very, very severe, whereas for this it's not. But even here we segmented the dancing bee in the first frame, and then it just continues. Otherwise, if you just do the motion thing, you will be tracking all the bees, and then you have to slowly remove the ones that don't follow the dance pattern. Okay, so this is the kind of so this is an example of what we call as behavior encoder tracking. Okay, because once you initialize, we don't worry about the other bees. We are able to maintain our track on only this particular bee that does this dance. Okay, so you can actually do those things by properly defining your likelihood and prior. Bayesian rule is the same. The thing that you learn in undergraduate probability, that has not changed. But what goes into the likelihood, goes into the prior, is the one that separates one from the other, right? So in any inference problem, if you have information about the anatomy, the object, the structure, the behavior, the motion pattern, Bayesian method provides a very nice mechanism and a vehicle for doing that. So I'm kind of a Bayesian by training, because I studied at Purdue, and when I was a student there from 77 to 81, we had the world's best pattern recognition group, and pattern recognition group was really moved Bayesian thing into practical applications. I mean, we had Fukunaga, Professor Fukunaga, you may have seen his book, Kingston Fu, the father of syntactic pattern recognition. My advisor, Professor Kashyap, who was big on pattern recognition of stochastic processes, and Patrick was there, Professor Tom Wang was there, so all these great professors, and I had fun taking their classes and sweating their midterms and so forth. But also, even then and even today, Purdue always had a great statistics department, and it was very big on Bayesian. Some of you may know that Professor Jim Berger is here at Duke. He used to be at Purdue when I was a student there, and he was also a very Bayesian. In fact, if you see his book, he will say all rational decisions are Bayesian and so on. So that's the kind of Bayesian I am. Okay. Okay. So this is one example of that. Now let's look at the approaches for activity modeling. Now, as I mentioned, we are more in terms of modeling movements, right, trajectories and this and that. There are many. If you take this has been going on for almost 15 years in computer science and EE and so forth. The statistical approaches, the ones that I like, the ones that Professor Krim likes. HMMs are big. People have looked at it for many years. Switch linear dynamical systems. People have looked at it for many years. And then, of course, graphical models. Markov chains can go here and here. and this is mostly done by AI folks, dynamic belief networks, Bayes networks, and so on, and then grammars and logic-based systems. And my colleague Professor Larry Davis is working on logic-based things. We do a little bit of grammar, and then we are more interested in this and that. Okay, now syntactic pattern recognition came about in the late 60s, early 70s, because it was realized even then that statistical methods are unable to capture structure. If everything you see is a vector and numerical attributes, then it's very difficult to capture structure, right? If you have a shape recognition problem, then shape has a structure, right? So you can have primitives, and then you can see how the primitives form together to make a shape, and that particular process can be written as a grammar, just like we have words and verbs and nouns and so on, and you make a nice sentence. So there is an English grammar, right? So K.S. Fu, Professor Fu was the pioneer in that field. But even and then once you have a grammar, then you can design your parsers. Computer science students, about the finite state grammar, regular grammars, and then context-free, context-sensitive, and so forth. And there is all the CYK parsers, early parser, and a whole bunch of them. So, Professor Fu and his students developed a lot of those applications of those algorithms for shape recognition and other kinds of pattern recognition problems where structure was important. One advantage is that even if you fail, if you look at the parser, you will have an idea of what the structure is, because you know what are the primitives that you have seen and how they are aligned and things like that. So that was the advantage. But it's an inference problem too, right? Now, in the case of statistical inference, we fit PDFs. Okay, so fitting PDFs is a little bit easier because there are a lot of great statisticians who have told us how to do that. Now, when you go to grammar, you pretty much still hand code them because there's no automatic procedure for inferring grammar for pattern analysis. There were earlier attempts in the 1974 by Taylor and Booth and so on. It's a very classical work for inferring grammar. So what I'm saying is, when you are in the inference problem, how do you come with a model is itself a challenge. HMMs, we understand that, so we fit that, but it's not always true that HMMs would work fine, right? And the same likewise. So grammar still has that issue of being able to infer the grammar, because once you have the inference, then you can do it. And again, in statistical pattern recognition, the class conditional densities, if they overlap too much, you have a lot of error. Right? Just take a two-class problem. Then I have one PDF like this, the other PDF like this. There's no overlap. You will have 100% recognition. Right? When there is overlap, where the regions overlap, that's where the error occurs, type 1 error and type 2 error. So in designing the grammar, if you don't ensure that the grammars for two different patterns do not overlap, if it turns out the production of one grammar can create the other pattern, then you are in trouble. Okay, so what I'm saying is, it's true when you go to syntactic pattern recognition, you have the structure, but the inference problem is still there. So anytime you go into an inference problem, the basic things that you had to face when you do statistical inference, you still have them. So when you go to the dynamic Bayes networks, belief networks, again the factor representations and all of that, how do you infer the models corresponding to conditional random fields and so on. It's all everywhere. So you cannot run away from the problem. It's just that in the case of purely statistical methods, we have a little bit better idea about how to do it. So the question here is, maybe inappropriate models but better mathematics versus, maybe better models but a little bit flaky mathematics. That's the judgment. I wouldn't call it flaky, but, less precise. So that's where the challenge is now. Sometimes when you have very large inference problems that involve structure and geometry, and the inference problem is very difficult, and sometimes people just say, oh, we'll just give these values to these parameters, and that doesn't work. So over the years we have done a lot of work, and I actually will pick and choose a few things and point out some of the key ideas that one should be looking at if you are interested in this field. Okay, so again here we have a humanoid doing some kind of let me see. Yeah, I don't know why that doesn't work. Okay, so what we did is we pegged some points on the scene, and then we made a little shape, and then we started analyzing the shape in terms of characterizing this particular activity. This was the work of Namrata Vaswani, and this is the video you saw, unconstrained one. Okay, now so the trajectories. So how much can you say by modeling the trajectories? That's what we are interested in. Okay, let's look at this problem. here I have a, I'll come back to the trajectory problem. Let me look at the human walking thing. Okay, so silhouettes I have, and I have these landmarks. Okay, and then an activity of walking can now be visualized as a sequence of shapes. Okay, so how do you characterize the shape? Now the walking also has some dynamical modeling. So it's not just bunch of static ones. There is some relationship among them, and you have to keep into account two things: view invariance, and you also have to keep into account rate invariance. Whether I walk fast or slow, it's still me, right? You have to keep both of them in mind. Let's assume that we take the landmark points and make complex vector out of them, x and y coordinates, right? And then you want to subtract the mean because it shouldn't matter where you are in the scene. So basically translational invariance. Okay, and then you also want to give some scale invariance. Whether you look at them close or farther away shouldn't matter. So after you do all of this, the resulting set of feature vectors, they have unit magnitude. So they lie on a shape sphere. Okay, that's the important thing. Okay, and so if you want to compare between two different patterns on the shape sphere, then you have to come up with better distances. Okay, that's one thing. All right, now in the early days, as I said, we were not very aware of differential geometry and so on. So we looked at approximations in differential geometry they make about what you can do in so-called tangent spaces, right? So you can linearize that, and so you can make it, this is a sphere and there is a pole, and you can put a tangent space there and dump all the trajectories that sit on this space onto them. Now how do these trajectories come? I have landmarks in each frame, so as I walk, these landmarks kind of dance around. So you have the trajectory. So they jointly characterize my way of walking. Okay, all right. Now let's see if I can do the thing on the tangent space. There are a couple of ways I can do. I can just match these time waveforms, providing for time warping. Time warping is provided because I may walk one day slow, I may walk one day faster, or the same activity I can do slower or faster. Okay, so that is one way to do. The other way is to just fit a time series model, okay, or a regressive model, ARMA model, and so on. Okay, so we have tried both. So when you do the ARMA model, then since you are in the tangent space, it's okay to do simple Euclidean measures for telling one ARMA model from the other ARMA model, and there are standard distance measures that are available. Okay, and those are something I'll actually list them later. There's a Frobenius norm, and there are many other norms for telling two different ARMA models. Okay, so we use that for telling between three actions. This is a very simple database. CMU and on the treadmill, slow walk, fast walk, and walk with the ball, and so on. And in the early days, we also did the same experiments we did for human gait-based identification. DARPA in 2000 had a program, 2000 to 2003, to see if there is enough information in a human gait for telling one person from the other. So they collected 120, they got a lot of data, 120 people walking along an oval track. There will be two cameras, and this sequence is viewed as the gallery sequence. That is like your training sequence. Okay, you have seen that. Okay, and then when they have this camera, they take a same video. It is what is called a probe, that is A. Okay, that is A. And when they change the shoe type, it is B. And then when they change the surface type and so on, they are here. So there are various kinds of probes, as they are called. So you see them with one camera, with one shoe type, with one kind of surface. And then when you see them again with a different camera, not too far separated, but pretty much the same baseline but separated, or with a different, instead of sneakers they were wearing some other sandals or something like that, or a different surface and so on. The idea is, can gait generalize across these variations? If they don't, then it's not very effective. Okay, so it turned out that if you train your subject on a particular surface, then when you see them on the same surface, the numbers were very good. When you see them walking on a concrete surface, the numbers went down. As you know, when you go to beach, you will be walking very normally on the concrete thing, and once you go to the sand, what happens? Everybody is kind of walking a little differently, right? Because that's the nature of the surface, right? So gait is very difficult because it varies with a lot of these things. And and somebody said, Rama, what will you do if somebody has pebbles in their feet and they walk, they're going to be limping. And I said, well, I'll watch their face. If they're in a lot of pain, I know there is something wrong, because I also do face recognition expression analysis, so it's not an issue for me. But the point is well taken. All these biometrics, you can beat them, okay? Just take the face recognition, right? You go to a bank, right? When you're doing this transaction with the teller, there are all these cameras. I know very often people don't want to sit there and, hey, I'm doing business. They all kind of slowly move because they don't want to be in the field of view. That's the human nature. You don't want to put your face everywhere. And the bank robbers knew for a long time that if they wore a baseball hat and a sunglass, it's difficult, because they wear a baseball hat, the camera is there, a sunglass, that's it, you can't catch them. Don't get any ideas, But I'm saying it's very simple to beat, right? So gait is also, but it's kind of interesting. There are a lot of other applications of gait analysis. Okay, so this is the professor rushing to class because he's late, and of course this is the student, right? That's what happens. So we have a motion capture data from CMU, and this is a very synthetic data, because you all these joint, these guys, these are all true data, where they are, so you can test out. It's not, because sometimes the errors you make in your low level vision algorithm in getting the silhouettes and the landmarks can kill you, okay, whereas here it's not an issue. So you can have 14 different kinds of walks. There is a crawl, there is a jog, there is a broom, sweeping one style, sweeping the other style, different kinds of, there's a blind walk and funky walk. That's what you saw. Prowling is like the Pink Panther kind of a thing, right? So you can separate all of those. And this is an example of why keeping track of the rate is very important. If you were matching two images, you have to register them properly before you can tell that there are any differences, right? So same, if I have one sequence, I walked and then suddenly I'm in a hurry, then if I want to walk them, you have to provide for time warping. You have to stretch or shrink the time so that you can match, so the frames align so you can match things properly. If you don't do it, then when you do this, you will have multiple heads and multiple arms and so on. It is true even in a simple analysis of principal component analysis, okay? So I take all of your faces, right? And then I want to register them first to a common framework, and then only I can calculate the mean, the covariance matrix, and do a eigen decomposition to find out what the principal components are. If they are not registered, they don't make any sense, okay? So registration is important in still image, and what is the equivalent of that in video is the rate, okay? That's the point. So what we did was, for each activity, you see one activity here, right? Standing, bend, and so on. For each activity, we figured out what are the possible variations that the trajectories can take. Then we characterize the space. So if you are looking at the action of walking, okay, you can slow walk, you can walk fast, you can even run if you want to assume they're all part of the same thing. And then you look at what happens to the trajectories around my silhouette when I undergo that motion. And then the trajectories have to go span a region, and that is what we call as the warping. Okay, so we can have event specific warping function. That means when you are matching, you have to kind of look for a match within this. That means you are still in the same activity. That's the whole idea, okay? Okay, so when we did that experiment with the USF gate data, see, this is A, B, C, D. So these are the probes, they are called. And this is with the left camera, same surface, same shoe type. Right camera, different shoe type. Left camera, the different shoe type. And this is changing the surfaces, and one of them is changing the briefcase and so on. So these are the numbers in terms of what is the top rank. It's not ready for deployment. If somebody is trying to ask you to invest in a company that can make millions in gate-based human identification, be careful. You won't get your money back because it's not ready yet, okay? But it's very interesting because we all have anecdotal evidence, and in addition to that, we are looking at many side problems. My daughter is 15 years old, and every day she carries about 10 pound of physics book, 10 pound of chemistry book, and 10 pound of math calculus book, okay? And I think most of our back problems we can attribute to all the big fat books we carried when we went to high school, right from junior high and high. I'm pretty sure about that. Okay. Anyway, so if we have a method that can tell if you give a human, okay, the weight and the body mass and so on, and then we can load the human and we can see what the change in the gait is. So I'm hoping to come up with a method where an anxious mom will send me a note saying my daughter is 5 feet 2 inches tall and 105 pounds, in weight, and how much can she carry today, and I'll go through my analysis and I'll say, well, don't let her carry calculus book today because she's going to break her back or something. We can do that. Second thing is, if people carry concealed objects, can you tell by the way they walk, right? I mean, it depends on how much. You can carry up to 40 pounds around your waist, and I know many who carry more than that when still they walk normally. So it's very difficult. But we had one of our research assistants carry just 15 pounds in one of his legs. We can catch it because you have the dragging motion, it changes the gait. Okay, it's easy to catch. So there are certain things you can do and certain you cannot. But there is a lot of interest. Backpack. This is what we call the backpack problem. If I carry a very heavy backpack, I can't walk like that. So I'll have to bend like this. So that changes the way I walk and whether we can pick it. So there is a lot of work we are doing on those things. Okay. All right. Let's look at the trajectory. This is the work of Namrata, and this particular activity, all the trajectories will get transferred here. And what we did was, in her work, she did this autoregressive modeling and so on, but she was more interested in abnormal activity. I mean, one of the passengers is pulled out here, or somebody will just loiter, will not move at all. A group of people will come and together and so on. So there are all possible abnormal situations that she was tracking. This turned out to be a much harder problem than we realized, because you have to define what is an outlier, right? If you want to define what an outlier is, and if the measurements that you have are noise free, then you are in good shape. But if the measurements that you are working with, they are also outputs of a tracker, that means they have errors. So when you have errors in measurements, how do you define your likelihood, or statistics for detecting outliers? It became a nightmare, and especially when all the tracking we were doing using particle filters. So if it is a linear Kalman filter tracking, then I have some idea of what the mean and the covariance of the position, velocity, the state vector, and then I can bootstrap something out of that in terms of error covariances and so on. But when you are working with a complicated thing like a particle filter, it became very difficult. So she did a wonderful analytical work and so on. So that is kind of involved. I refer you to her paper that appeared in Signal Processing Transactions in 2005, and the one I did with error image processing in 2004. Those are good things. Now, of course, if you are not keen on doing such complicated statistical methods, then one computer vision technique that you can look at is take this trajectory, right? This has a shape and a motion associated with it, okay? Shape and motion. And you can use what is known as a factorization theorem. What it does is, as I walk, suppose I have 100 points on my body. I track these over the frames. I construct a big matrix. And then you can do SVD of this matrix and break it up into a shape matrix and a motion matrix. For orthographic projection, this is beautiful. Theory is very simple, and this is the classical work of Tomasi and Kanade. Professor Tomasi is not too far from here. He is a Duke. And then Chris Bregler developed it for non-rigid bodies and so on. That means if you have articulated motion, what you will have a basis shape for each such motion, and then you will have characterize the entire motion as a sum of those motions. Now, if you have a video where there are multiple activities, you can view each activity corresponding to one articulating motion and so on. So you can apply non-rigid factorization theorem for characterizing multiple activities in a scene. It is very effective. It's very simple because the math is very simple. So close, SVD is MATLAB, right? These days, things that make name are the ones in MATLAB. Because none of my students want to do any more C code anymore. How about you guys? You do any C code or it's all MATLAB? And so what is in MATLAB is what is getting into your program, right? So, think about it. In MATLAB, they don't change every year, do they? So it's scary. But the point is that SVD, and you don't have to even think about doing it. It is in MATLAB, so you can run it, and it works very effectively. We had a paper in CVPR a couple of years ago on this, so that is worth doing. Okay. Now let me get on to this manifold things, and why is this important? If you have certain types of features that you are using, and if you know these features have certain structures to them, it makes sense to use distance measures that appropriately represent that structure. So if it turns out that I'm separating me from somebody else by using an orthonormal matrix, somehow I can be represented by an orthonormal matrix, okay? And then you want to come up with a measure that is very good for separating one orthonormal matrix from the other, and therefore you can see where all the set of space of orthonormal matrices lie, and the differential geometry guys have a name for it. They call it the Steffel manifold, the Grassmann manifold, and so on. Okay, so slowly we started looking at these for some of our problems. So what we did was, remember I talked about the Procrustes distance measure. Okay, now we developed a manifold version of that by using this standard calculations, because we said okay, Procrustes distance point on this class of orthonormal matrix is an equivalence class of these matrices XR, where R is a full. So for a Procrustes distance x1 x2, you can calculate the minimum distance between them in this way, and so the smallest squared Euclidean distance between any pair of matrices is the corresponding equivalent. So you are converting the thing that involves manifold in terms of Euclidean distance by introducing the intermediate matrix R. This is a standard calculation for identifying Procrustes distances, separation between them, and then we use that for INRIA data set. There are all these activities: checking watch, cross arms, scratch head, turn around, sit down, walk, and so forth, and 11 actors performing 13 different actions. Okay, so it's multi-camera data. If you are interested in activity recognition, this is a good data set to have. Okay, from INRIA.
So what do you do when you cross arms? What kind of video is that?
No, it's like that.
That's it? You
Yeah.
just sit there?
Yeah, they're not moving. It's all stand.
Oh,
Yeah, they're not.
It's a video sequence.
Yes. Okay. Now you can try principal component analysis and this and that. Okay. So when we did the Procrustes distance, so remember I talked about autoregressive model, and then subspace angle is one way of separating distance between them. And then Malnabis distance is another way. And this is the Procrustes distance measure using manifold computations. And here, when we had multiple examples of the same activity, we can actually fit a PDF. So remember, when you have multiple examples of the same activity, you can actually build a PDF. You have multiple realizations, and you can build Gaussian, mixture of Gaussians, or you can even do a kernel method and so on. These are standard techniques. So 98.78, and on the data, well, INRIA, when they first came out with this data a couple of years ago, everybody was struggling here. Now slowly it has become 99.99. So they said the problem is too simple. I always tell, when you are working in pattern recognition, never submit a paper with 100% recognition. It will not get accepted. Right? If I review, I said, must be data is very easy, because we don't believe you can do 100%. So the moment you are between 85 and 90, that's when you have to submit your paper, and then we have respect for it. But if you do better than that, you start a company, not publish, because if you come with 95 and above, we will reject your paper. We don't believe that. Okay? So I know it's being recorded, but it's all right. So anytime the performance is better than 95, you start a company and make a lot of money. If it is between 85 and 95, you submit and get a transaction paper. Yeah, you heard it from me. Okay. So, and I also say that if the data set doesn't change, as we start working more and more, we get better, because we understand the data a little bit better, right? So it's not surprising, but it's a good thing. And then we also try to do a face recognition using dynamic texture models. Okay, suppose you have this is a face, right, in a video. Okay, I can write the features, and I can write I can have a motion model for the face, in an affine motion model. That's what I'm coding here. This will be the appearance of the model. Okay, that means actual phase that you see, it goes in here, and then we can use this matrix itself, C matrix itself, as a way to characterize one phase from the other. Okay, and then if you look at the C matrix, the way the decomposition is done is one can show it is a class of orthonormal matrix, and therefore it lies on this guy, and then you can do recognition, and again, you know, the numbers are pretty good. Okay, so so the so-called, I talked about a lot of methods that had some parametric nature to it. Suppose I don't want to apply any parametric methods. I'm given a video segment like a tennis match. I don't know how to characterize, you know, the serve, you know, versus the backhand and the forehand. But I know there are many different things. So I would like to first see if I can come up with a method, okay, without any supervision, that I can all segments corresponding to the action of serve can all somewhere map here. Okay, again we have the same shape sphere and so on, and corresponding to backhand and volley and all of that. So how can I do that? What we did was the following. I'm a signal processing guy, so whenever I have an opportunity to fit some time series models, I never shy away from them. But that's not going to just be enough. So you can fit models for the way these points all change. This is a UCF data set where they take something from this cupboard and put it on the table and so on. Okay, now we just fit optical flow. We took the the movement, segmented the movement, and then we fitted optical flow for the x and y component, a set of models like this. Is standard time series models that most of you who have done signal processing courses will know. And then our point is simple. We will take short segments and characterize as a linear time invariant system. Okay, and then as we are fitting, we will constantly evaluate when the new frame comes in, whether the motion pattern of the new frame, as determined by the optical flow, belongs to this model or it is a slightly different one. That means you should have a method for fitting a model, and then you should have a method for telling whether something belongs to this model or not. Those are standard things. Then I have a next segment. The moment I know the new frame doesn't belong here, I start my next model. Okay, and things like that. So you start this video and you are doing this series of linear time invariant systems, which is an easy thing for a EE. That's what you learn in your first year of graduate school, how to fit linear time invariance models. Okay, but then I also want to have a method for checking if there are repetitive actions. You know, in a sports video like tennis, there are same things are happening, although from slightly different viewpoint, different rates and so forth. So if I want to compare this serve segment with some other serve segment, I have to make sure that there is some amount of view invariance provided, because the next time the serve may not be the same way, right? The people, they stand in the same place, but they're a little different, they're orient a little different. And also the first serves are coming with the big boom, bang, and the second one is a little slow. So the rate is different. So you have to provide for such invariances, rate and view, when you are comparing two such segments. Otherwise you will make mistakes. So that's the new thing we did, and I'll talk about that. Okay. Okay, so if you look at the optical flow, see, this is the action of serve. Okay, so this appearance will go here, and we'll have a very simple motion model, affine motion model, because that's what we have for the optical flow, and we do that. Okay, and then you have these model parameters, and you can estimate them by using standard singular value decomposition. Again, it's these are the works done by Professor Suato and many others. Okay. Okay, so these are the three distance measures I mentioned before. Okay, they're all somewhat related to the so-called principal angles between column spaces of observability matrix. Again, if you're familiar with linear system theory, when you fit models, you can construct these matrices and get these angles. All this does is to say whether this model is same as this model. If it turns out that you were always observing the tennis player the same way with respect to the camera, and if the player always played the same way, whether it is a first serve or a second serve and so on, then you don't have to do anything more. But it never happens in practice, so you have to provide for some invariance. And before that, If I don't know how many number of clusters I have, then I can calculate this pairwise distances between all the segments I have. I throw them in a matrix and then I can permute them and so on, and if there are only two, then you will see that some of them will cluster here and some will cluster here. This is again coming from what is known as a multi-body factorization approach. That's from Chris Bregler's group. Okay, all right. So view and rate variations. Okay, so what you can do is you can look at what happens when view changes, whether it changes matrix C or matrix A. When the rate changes, which matrix changes, and then you incorporate for those changes. It's easy to show when view changes, appearance changes, not the rate. So therefore matrix C is what you want to worry about. When change in execution rate, matrix A is what you want to worry about. Okay, and then you can make this transformation. So I have F1 corresponding to view 1, F2 corresponding to V2, and we are assuming the same rate. That means these two matrices are different. So when you're comparing the parameters, these two, you have to take the parameters of this and run it through the transformation that links C1 and C2 and match it. That's like what you do for shape matching and so on. All right, so to the corresponding principal components, which are nothing but matrix C, they are also related by the same affine transform. So you can estimate what the affine transform is from the C matrix itself, because corresponding to the two different views, they are related through the affine transform. Okay, likewise, when you look at the rate, what happens is, since A codes the dynamics, A1 and A2 will be different. Now you can figure out what the time warping you need to do by looking at the eigenvalues of the matrix A1 and A2, taking the log and the ratio and so on. So this is all described in our CVPR 2007 paper that was given in Minneapolis. Okay, all right. So now I have the rate, I have the view, then I can just compare them. So I have sequence 1 with A1 C1, A2 C2. That means different view, different rates, and then you have to compensate for them. It's like what you would do in a regular still image based shape matching problem. You have rotation, you have translation, you have to account for them, right? So when you match, you look for all possible rotations so that the match can be the best. Okay, and of course when it comes to video, there are a lot of other things you have to worry about. So my student did all of that. So let's see if how this one works. So these are the kind of, we worked with the skating example because the tennis example is pretty bad. You look at so much background motion and so on. Our algorithms are always getting into trouble. But skating is good. Once you segment the person, the contrast is pretty good because they almost always wear very dark clothes. So we can automatically segment. Our goal is this. Suppose first we get these segments, and then an expert in skating will come and give names to these. So next time we see another skating video, we will again unsupervised manner segment them and then find out which are the parameters that are closer to. So one particular segment is closer to this, then we will take the name from here and we'll attach it. So you can actually name a video. Okay, and you will be effective if you provide view and rate invariance. Otherwise you will have a lot more clusters than you need to have. Okay, so that's one application. So this is what's called as providing context to a video, right? So but you still need an expert. So before I finish, let me show this example, because in computer vision, an interesting thing is sometimes you can have a lot of interesting mathematics and very complicated things and fine. And sometimes you can look at a problem and come up with a 10-line MATLAB code and which works just fine too. Here we are trying to find out an unattended package. Okay, so we do three kinds of motion analysis. We always track the humans because they carry the package. And then if somebody is standing in one place, the human doesn't move at all, absolutely standing still, then we declare him also as an unattended package. That's part of the problem. Of course, then if somebody leaves the package, we can detect it. Just three kinds of motion analysis. Okay, so look at 28. Suddenly he'll be just looking at his BlackBerry and he'll not move at all, and then we'll put a red border around him because our algorithm cannot separate him. See? The guy doesn't move. He is like unattended package. But the moment he moves his hands, then he will take him off from consideration. Okay, so there you go. And now we'll wait. This was actually taken in a Munich airport. And Siemens, we were working with them on a DHS project, Department of Homeland Security project. Okay, so there you go. Okay, so, but the police didn't care. They didn't ask anything. So, you worry about the security, right? So, this is to just show sometimes, you can design some very practical, simple solutions which are just as effective. But it's not to tell you that you should not read mathematics and so on. You should, because that is still fun, But vision is a very interesting field. Sometimes by just coming up with a clever method, you can really do very well. Need not be extremely complicated. I mean, shape analysis has been there for a long time. A few years ago, professors at Berkeley came with a concept on a shape context, which is a very simple context, and it's extremely powerful for many applications and so forth. So those are examples of that. That's the nature of computer vision, right? So you have to hit the right representation, right analysis, and so on. Then you will be fine. It's one of the most interesting fields to work in. Not because I am working in it, but yeah, it's because I think Professor Krim is working on it. And that's what I said. But it brings in all kinds of mathematics. Statistics is important. Probability is important. Shape is important. Motion is important. Texture is important. And where you are is important. Light source is important. Where you are looking at from important. The new sensors. It's just amazing. It's just so difficult to keep track of it. So if you are working in any research area other than computer vision, I will encourage you, all of you, to just move into computer vision. Yeah?
Good advice.
Yeah. It's just a beautiful subject, especially if you like inference. Okay, so patent discovery. And also if you have a great company with that product, Google will buy you. 10 years ago, everybody started a company thinking Microsoft will buy them, right? Microsoft went for Yahoo, Yahoo said no, right? So now Google, the company that did best in the face recognition vendor test in 2006 challenge, I think it was bought by Google. So now if you want to start a company, make sure you start a company that Google will be interested in buying. That means patent discovery in video. They're very interested in that. Okay? That's a good advice?
Good advice.
Yeah. All right. So thanks for your time. I know it's a little difficult to stay awake right after lunch. I don't know how many of you had lunch. No. See, they did the good thing. They're going to eat lunch now. Good. Thank you. If you have any questions, I'll be happy to answer.
Any questions?
Yes.
My question is related to time warping.
Yeah.
Now, I suspect that the problem is not playing the motion in regular speed and then hitting the fast forward button. It's not that at all.
No, it's not.
So what are the extra challenges, and how do you overcome them in practice?
Okay, the fact is that I can walk slowly like this, right? The trajectories. Okay, you're sampling with the same camera, and so and then suddenly if I walk very fast, and then you have to align the frames. So that's basically the issue in terms of time warping. Just like in speech. When you say, Chellappa or Chellappa, so you have to match those two things, and the waveforms will be different, right? So, so the rate invariance, all we did was when for that we didn't fit any model, we just took the appearance feature vector, and then we have two sets of vectors, temporal sequences, and then we adjust to see if we can compress or expand. We take one vector and then we try to compress or expand to see if it matches the other one. And how much you have to expand or compress depends on the particular action. Okay, so we try, suppose we think there are 10 actions, right? For each action we have their own warping space. So we try to change the trajectory when we match to keep the variations within each one of those, and then we can say, to the extent the trajectory I see, and when I vary it, it matches best within this warping area, then I consider this a walking motion, I consider this a broom, and so on. So that's all there is to it. Is it clear, or?
Well, my question is
Yeah.
the dynamics of motion would change from me moving my hand fast enough, or me being
Slow.
conscious of it.
Sure.
Which
That's why I remember the two matrices A1 and A2, they are different, but we know how they are related.
Okay.
The Q, how to warp one matrix to the other matrix, you can estimate from the eigenvalues of A1 and A2, and that's the number I gave. So that is then you have to adjust for that. Okay. Yeah.
Any other question?
if I have a question, if your camera is moving, like how how is a better method to actually, like, there's a possibility of having the images that are like maybe there's some shock on the path or something like that, and the images go totally like haywire.
Yeah. No, when the sensor is also moving, there are different techniques to do. We are also working on micro air vehicles, right, tracking and so on, and I can show you some examples of that. You have to do sensor ego motion compensation, and then you analyze the residual motion. Okay, I'll show you some examples of that. And then these days we are able to do better and better, because in addition to video sensors, which were the dominant source before, we have inertial sensors on the platform, so we can initialize the stabilization results using that and so on. Okay, so it works out fine. But you have to remove the sensor motion, or the ego motion as it is called. Let me see this. That's the one. Yeah, so I think I have to go to the so this is a simple example of a tracking vehicle.
Yeah.
Okay. Now here we stabilize, or what we can do, we can simultaneously track the motion of the sensor and the motion of the object. You can create an expanded state vector, that also works. And there are so here we can, this is from a UAV Predator, right? So we can just track people if you want. We can track people and vehicles. And we also have done the following thing. Suppose you are given a 10-second video, you learn as much as you can about the object, and a few minutes later you are given another 1-second video, so you have to tell which one of the objects you saw. This is called video verification and identification, and that's important, because next time when you see, the object will be in a different pose and everything, right? So we quickly learn something about the object, we build models, and we synthesize novel views, so the next time we have to match across those views. And we worked with SAIC on that, and they did a lot of experiments, and so similar things. So you have to take into account the sensor motion, and there are many ways to do that. Yeah.
Any other questions? I have a question.
Yeah.
I'm still hung up on the normal and abnormal stuff. Are you working with like a psychologist or something that kind of
No, yeah,
analyze?
we are looking into that. See, the thing is this. This is very domain dependent, right? What is normal, abnormal? Okay.
Right.
In the case of tarmac, the TSA guys told us what to look for. For example, if it is required that a fuel tank should come in service, and if it didn't show up, you may laugh. Things like that have happened. The pilot thinks the fueling was done, he goes, and after half an hour he says, oh my God, I don't have any, and he lands somewhere, right? So that's a clear abnormality, because there are certain times when they have to come and do it. So, that is something you can watch for, over a period of a day. And passengers not being allowed to move in certain areas, that is easy to track. Okay, that's an abnormality. And then
Suppose you're surveilling like an area, say like a terrorist putting a bomb somewhere or something like that. That's what I have in mind.
Well,
in terms of
yeah, I don't know. I mean, that when they want to do such nasty things, they do it so that it looks normal. So that is hard to find out. But there are still attempts to look for digging operations and things like that. So some of the activities that are being discussed at the new DARPA BAA on Virat is digging operations, shooting, and things like that. Yeah, so those are some of the things you can look for. And if if a lot of people are going in one way and somebody is going the other way, that's an abnormal, right? That's what Eric Grimson did in the late mid 90s as part of VSAM. Abnormal patterns, or people taking U-turns where they should not be taking U-turns. That's an abnormal thing. So if you have traffic cameras, if you are looking for that, you can do that. That's a very clearly defined abnormality, right? Nobody should be taking U-turn, or left turn, not left turn. So I think you will see soon local police looking for these kinds of violations, because it's not anymore privacy. They can't read your they can't read your license plates. They just want to look at the flow. And right now they are giving tickets left and right in Maryland, in Montgomery County. Near schools, if you go more than 25 miles, you are getting a $70 ticket. They just have a couple of cameras, and it works beautifully. You see a flash, and 2 days later you're going to write a $70 check. Now they can do more. I mean, whenever it says no left turn, all they have to do is put a camera there and watch for people taking left turn and take a picture and send them a bill. Vision can make money. So that's an abnormal event, okay, right? So no U-turn, things like that. Do not enter. So those are all well defined. In terms of traffic patterns, it's very understood. In terms of humans, it's very difficult, because humans are difficult. So they do. When you tell them not to do something, they'll do that, and they will make it look like it's normal. So what do you do? Yeah. So but it is a very difficult problem, though, because it's very subtle. You don't want to have too many false alarms. Okay. So.
Well, if there are no more questions, let's thank our speaker again.